Okay. So should I should I start?
Yeah.
All right. There was an incredibly heavy rain here actually a few minutes ago. It just fortunately stopped. So, all right. So this is Tsunami Waves. And someone pointed out to me how stupid the title was, which I thought was a fair comment. So it's it's in fact not going to be only one very small aspect of Tsunami Waves, which is how they're generated. And this is joint work with Santu Das, who's a long-time collaborator of mine. And he brought this problem to me, and both of us have become really interested in it. And it's a surprisingly understudied problem. I think it's the thing that's remarkable about it, given how important it is. So I'm going to show a movie of a tsunami being destructive, which will be quite fun for us to watch. I'm not sure if I managed to, if I'll be able to share the sound when I play it, but we'll see what happens with that. So we're interested in what the problem I'm interested in is how these tsunami waves are generated and whether they, in this process, they generate what are called acoustic gravity waves. So this acoustic gravity waves has been the subject of study by one group coming out of the Technion in Israel, and they seem to be the only people that are sort of interested in this problem, and they and members of that group have postulated that they can be used for predicting tsunamis and all kinds of things. But essentially the acoustic gravity waves, because we in the wave community we kind of understand these, they're the evanescent modes get transformed when you take and if you allow for compressibility, they can become traveling waves. And you need a lot of, the water's not very compressible, so you need very high frequencies and very long wavelengths, and only something like a tsunami can move the waves. You couldn't make these acoustic gravity waves in a waveform, not easily anyway. And I've written here that the fundamental mathematics is surprisingly poorly studied, because it's one of the things that's, throughout this whole work, I just keep having the feeling that surely somebody has already worked all this out. It's just like none of that would surprise me. But so far I haven't found it. Although so far we haven't gone much past what these guys did in this group from the Technion, from Stiassny, from Michael Stiassny. We haven't gone much further than what they've done. We've added a little bit to it, and we've done a bit more numerics than they did. Okay, so I'm hoping this is going to play. I'm not sure you can hear the sound here. I presume not. So this is just the footage of the tsunami coming in. It's got actually nothing to do with the rest of the report. It's just one tsunamis, but it does give you a sense of all watching this. It's quite exciting. So here's this guy's are looking out. What was he felt the earthquake? So maybe they're expecting a tsunami. I think these boats have been told to get out to sea, which is a sensible thing to do. You don't really want to be in this environment, but unfortunately they've gone a bit late, and you're going to see something. What happens here? So this is the sort of shelter up, and suddenly the water is just pouring over this, pouring over the breakwater. It's hard to see here. That it doesn't look too scary at this point, because this is about this point. Every time I watch the video, I think it just sort of transforms at some point. Let's go over here. Not quite sure why they go over here. We don't really want to see that. That's some sort of floating dock that's obviously in grave danger. Those cranes are going to have a lot of work to do shortly. And here we go. There's the wave starting to come in, like these beautiful waves starting to break. Really fascinating why we form this beautiful, perfect long wave. And then whoops, it's really bad. That boat, you should not get sighted like that. And that's the last we see in this video. A bad feeling about it. And then you just see the water pouring in, and it's as if a magician had just commanded the waters to flow onto shore, isn't it? Like, you can't really believe that that's just being driven by gravity and by water's desire to be flat. That just makes no sense. It's just sort of pouring up as if under the command of some, wizard. And then here it is here, this has just turned into the seething ocean. And those boats should obviously try to get out of here very rapidly, because all that water is going to have to come back out at some point. It's also going to cause some problems, you'd imagine. It wouldn't be that great a place to be. But just get a sense of it, how crazy they are. And there's that floating dock there just getting slightly destroyed. All right, the movie finishes there. So I'm not sure how much I'll play of this next video, because I don't think you can hear the sound of it. But it's a funny sort of maybe you can hear the sound being played through the.
Like, there should be an option to share the computer sound, maybe at the top of the screen.
I was playing the sound here off my computer, but probably blacking that out. You can't hear it here.
We can't hear it, no.
Oh, okay.
Can you share, like at the top of your screen, if you just sort of scroll up to the top, do you see a little sharing bar?
Yeah.
Yeah, in the middle, that little one, that little box, that little box.
Requiring installation of early tsunami detection systems.
Allows it.
Yeah, so that one you clicked, Mike, that little one.
This one here.
This is a challenge.
That's right, that's right.
Okay. Let's see if we can play it again, or it's a bit dangerous. Yeah, I suppose we can go.
It's working if you have that share sound clicked.
Okay, thanks a lot. I'll do this here. It's a bit dangerous, but I'll just try and play it directly here.
Giant sound waves could subdue tsunamis. The devastating impact of tsunamis.
Well, it's not going to allow me to move that. All right. Okay, that's very depressing. I'll just carry on here.
Mike, I think it's okay if you play it in the presentation, as long as the that share box is ticked at the top of the screen like you had before.
Yeah, the problem is I'm worried I'm going to have to. It's not going to. Doesn't seem to want to play it now. In the presentation. Technology. It was quite a funny video because it's all bullshit, and I quite enjoyed it, and I quite enjoy showing it. It'd be interesting. So we can start again, I suppose, but the problem is it might end up playing both the movies. All right, I think I'll see if I can play it at the end, because it was interesting, and it's a kind of a bullshit thing all about how you could use these acoustic gravity waves, and it's a funny path that one of the people studying these went down. I don't quite know why, rather than sort of doing the fundamental research. It's just odd how research works here, and why this problem's been left. But what the problem we're interested in is very, very simple. We've got a two-dimensional waveguide. This is just showing you something about the tsunamis. We don't really need to. You guys know how powerful it is. If you can lift 5 kilometers of water up by a meter, that's a massive amount of energy. Like, it's unbelievable. It's like an atomic bomb type of energy. And even though at the surface you'd hardly see a thing. So what we're interested in is this problem of, and I'll show it in so there's basically all the same equations you'd be familiar with, except we allow for the compressibility, but that doesn't make a lot of difference. And that only kicks in. We're going to use the speed of sound for an actual water. So it's only going to kick in when the water is really, under certain conditions. Okay, so what we're interested in is a two-dimensional waveguide with a free surface, and we move the bottom of the surface between minus B and B. We shift that in some arbitrary way, and we basically lift it up by an amount. In the most simple case, the whole thing between minus B just lifts up uniformly. And then what are the waves that are generated by that? And how do they propagate away? And I'm going to show some numerical simulations of that. So it seems like a super basic problem to solve, and clearly it's important to understand that and how this wave generates. So it's only a two-dimensional. We've got to extend it to 3 dimensions. And we're going to do it by a relatively simple process. We're going to solve the frequency domain problem, we're going to write down an analytic solution to that, and then we're going to write down the time-dependent solution by a Fourier transform. And what the work that went before, the only thing I'm really adding to it in this instance is I'm going to do the numerical computations and create these simulations which haven't been seen before to the best of my knowledge, and I'm going to do it for an arbitrary undulation here rather than just for a square. But and the solution method we follow is one that was established in 1982, and this rather it was done by this very unwell-known researcher from the University of Miami, and it was only recently really become cited or known. So it's kind of, he wasn't working in ocean waves, he was in tsunamis or something like that. It's a rather odd sort of situation. Again, it's strange what happens in the literature. We tend to follow each other. It's a, so, we know that with the way citations work on papers and things like that, so there's a power law distribution to it. So this paper got forgotten, but of course it was finally, because the work is so important or so fundamental, it didn't get rediscovered, which is fortunate. At least that's what I'm thinking. All right, so we can solve this following this method of Yamamoto. We just take a Fourier transform in space. And we end up, so if we take a Fourier transform, we end up with the solution, Fourier space looks like this. Okay, that this is not the time-dependent problem, this is the frequency domain problem in space. And we end up with this expression, and we can solve this by, we can find the inverse Fourier transform here by contour integration, which is really beautiful stuff. And the only difference between what happened before is we've added in these sinusoidal ripples, so we have an m pi here, whereas the literature previously only contained the m equals 0 solution. Okay, so there's the solution, and then this other part of it, this D part, is just the dispersion equation. So you're going to pick up poles from here. So we can write down the solution. The only thing that's you got to be a little bit careful about is how you do this contour integration, whether you go under these, why you go under these poles and over these poles. And it's basically just to impose a radiation condition at infinity that the waves are radiating out. And what happens is that normally you'd only have one solution sitting on here, one travelling wave, but if under certain conditions, the evanescent modes, the first so many of the evanescent modes can get converted to travelling waves. It's just like the sort of cutoff frequencies in waveguides. It's like the fluid is like a waveguide, the free surface. So when you apply that, you get this formula here. So, and the m equals 0 case was done by this Yamamoto in 1982. So this is this paper that I was talking about, that all of this work is based on. So that's only the frequency domain solution. But it says to you what happens if I take that bottom and I oscillate it up and down. And if I oscillate it up and down and with a cos or a sine as well, what solution do I get? And you get this. This is the solution here. So these are the travelling waves. And these are also travelling waves. These are these modes that have got converted. So there's n of them. N may be equal to 0, right? There may be none. But the first so many of these modes can get converted into these acoustic gravity waves. So these are waves that propagate. These are evanescent waves that propagate rather than decay. Okay, because we've got the fluid being compressible. And that's only going to happen if we have really deep ocean, and we need to get that to happen. We need high frequencies and large wavelengths, which is only going to be produced by a tsunami. And these are the evanescent modes. Okay, so there's a solution. So we've now got the frequency domain solution. So we've got to work out the time, and there's the solution under it, which is really interesting as well how this works, because you get two solutions inside and outside, and they come from the closing of the contours gets sort of shifted as you jump. And you get a slightly different, you get a different expression under, and they have to match. So just the first thing you can do, when you compute these solutions, is make sure that they match. And this thing here has this particular solution that appears, that kind of is what's driving the motion itself. And you could find this by eigenfunction matching for the m equals 0 case. That hasn't appeared in the literature, but given that I love eigenfunction matching, I obviously went and found that and showed that it was the same. And the derivation is actually beautifully simple with eigenfunction matching. So that's, it's quite cool. But of course, so we re-derive Yamamoto's 1982 solution by eigenfunction matching. All right. And then we just start using some Fourier series to do an arbitrary shape. I'm not sure how important the arbitrary shape is, but that's kind of cool. And so we don't have to just make the bottom move uniformly. We can add like a Gaussian pulse or something, and then we apply this Fourier transform in time to solve it. So now the Fourier transform and the Laplace transform are the same object. It's not helpful to think of them as different, I don't think. So it's just as cos is to cosh. But the Fourier transform I think is better. I prefer the Fourier transform, given they're the same. That's a bit of an odd comment, but the Laplace transform wants you to use this analytically continued omega that decays really rapidly, and it sounds great when you do the transform forward, but you pay a big price going back, and you get this Bromwich contour, and it can be a real pain in the neck. The conversion property is really nasty, but if you're prepared to do the transforms both ways with an I omega, it just balances better, in my opinion. It's a better meet in the middle. So, so that's what we're going to do here, and perhaps this is my expertise is really in producing these integrals. So I think this is one of the things that reasons why people maybe haven't gone on here, because it's really simple to do this integral, but there's a couple of tricks. I'll just come to that shortly. So there's the solution here. So we have some arbitrary motion of the bottom. We allow the bottom to rise uniformly at some speed, you know, from 0 to 1, but it rises in 1 second, 10 seconds, or 100 seconds, or a zillionth of a second. Just adds a little bit of arbitrariness to it here to this. So there's our function in Fourier space, and then we can now just do an inverse Fourier transform. This just weights the transform. And there's the expression there for the solution. So this is all analytic in a sense that all you've got to do is solve some transcendental equation to solve the roots of the dispersion equation, and you get this expression. And this trick here is really important. This conversion to the real. Every time you have these Fourier integrals, have a very good look at it and make sure that there's usually some symmetry, because we know ourselves that omega can be positive or negative. We're still arguing about that. So the solution for positive omega is the same as the solution for negative omega, plus or minus some conjugation. So we only want to do the positive ones, take the real part. And that doesn't just save you a lot of work. This integral can be really poorly convergent. The convergence properties of this integral here can be an absolute nightmare, will not converge. Just forget it, you're going to be struggling forever and hating it. The computer's going nowhere, and this integral can converge really rapidly. It's very odd why that is. Okay, so once you've done that, away you go, and you can make some calculations. Now, unfortunately, my slides aren't. Oh, here we go. Here's a picture of the slide here. Okay, so what happens is I've got an. This is working. I don't know why it wasn't working before. So I just very rapidly, this is what this is showing, I pulse the bottom surface with a Gaussian profile, and I get these two pulses that split apart. And this is 1,000 kilometers depth, and it's a 40 kilometers wide. Well, you can see here it's not 40 kilometers. I've lied about that, but it could have been 40 kilometers wide, but it actually sort of stretches from about, what, 15 to 15. And this is completely, all that's happened is the surface of the water's risen up like that, and then it's broken into two simple waves that move apart. Okay, that's what so you got the shallow water, incompressible, compressible. You don't need any of this fancy theory for that. So you don't see anything interesting. It's just which is kind of, you know, in itself interesting. This is 500 seconds later. So this wave's traveled in 500 seconds. It's traveled 50 kilometers. It's moving fairly quickly, like jet engine type speeds, right? As we know tsunamis do. Okay, so that's really great, because that actually tests our theory is correct, and we managed to show that you can, under all kinds of terrible limits, you can derive this. This is just D'Alembert's solution of this thing. It's half the Gaussian going in both directions, and we've got this incredibly horrendous formula that we found that when we compute gets that. So we must be able to crank some terrible handle mathematically to show that, and sure enough we can. Now, I don't know if these are going to play here. This is the problem. I've had a lot of problems playing these movies, and I mean, sort of, I don't know what's going on here, but what I might do, you said to me here, if I stop presenting, let's go here. I'm going to try and show you these just directly, if that's all right. Because there's just one movie I really wanted to show.
Michael, you are not sharing your...
Yeah, no, I'm not. I'm just trying to get it so I want to share something else. I'm just going to directly share the movies here. So they've really been misbehaving. Okay, I'll try again now, okay? Sorry about that. So I think I want, okay, good grief. Which is screen 1, which is screen 2 is the next question. Oh my God. That's not the right one. Here we go. So I'm going to show, if I can just show this one movie, I feel happy. Here we go. Okay, brilliant. All right. So what this is this is a much more interesting case. Okay, so it's not a Gaussian, it's just a square pulse. So we didn't only really need a Yamamoto. But let's see if I can play this. Okay. Here we go. Brilliant. All right. So there it rises up, and then you see this. That's the blue dotted is the blue is the shallow water solution. And there's that wiggling is just numerical error that we've got. There should be a straight line coming down here. It shouldn't be a block because it took a finite time to rise. And the green is this incompressible solution, and the shallow water and the red is the full compressible solution. So you see this crazy thing here where the whole surface is bouncing up and down. Like, is that right or not? When I first saw that, I thought, oh my God, I just made some numerical error. But actually, it turns out that, just remember the scale here. This is kilometers deep, and this is just 5 kilometers deep. This is 1 meter here. Don't confuse. This is just the illustration, okay? So this is miles away below the bottom. Okay, but of course it's much wider. But what happens is that at some point suddenly the compressibility becomes really important, and it switches on, and you get this bizarre behavior, and you get a compressive wave that travels from the bottom up to the top and reflects. And it actually it's got to go up, reflect once, come back, reflect, and go down before it. So that frequency of oscillation is 4 times the depth divided the speed divided by 4 times the depth. But that's the first time that that's been reported or seen, and I believe it's real. So that the solution, there's this compressive bouncing of the surface. And I'll just show this once more. You can see here that there's these waves that rush away ahead of it. These are these acoustic gravity waves that you could use to predict the tsunami, and they are moving like a rocket. Like, this is 10 seconds, this is 100 seconds later, and they're miles away. They're 200 kilometers away. So they're doing 200 kilometers in 100 seconds. That's fast. So you can see the idea. Of course, this is all 2-dimensional, and 3-dimensionals, they're not huge amplitude, they'd spread out. And if the tsunami rises slowly, you'd never see them. You'd have no effect of the compressibility. It's got to rise quickly. And it's actually very hard to know how quickly and over what area that surface of the bottom of the ocean's moving when it generates a tsunami. That's actually something we found really hard to find. Okay, so I think I'm presenting this. I'm not sure what I'm presenting here. All right, I've done enough here. Sorry about this. Those movies not working. It's rather frustrating, but I'll try and come back up here. I had a whole lot of other movies. There were stacks of them. They actually got really boring, to be honest, but I loved them because I spent so long making them. So you haven't missed out on too much. There we go. We've obviously only done it 2 dimensions.
Sorry, Michael, we can't hear you. We lost your voice. Hi, Michael. Hi, Michael. We can't hear you. Hi, Michael. I think we missed your last few words. Hello? Hi, Mike.
Oh, yeah. Well, now if I play them, but now when I booted that up, it started playing the video with the sound, which I turned off, so I couldn't hear you. There's some reasons to be in the room with some point.
Yeah, Mike, we lost the last few words from you, and yeah.
Okay. Yeah, I was just going to say. Basically, I was saying I'd finished. I think.
Okay. All right. So we open for the questions.